All right. Hi, guys. Welcome back to Recitation 0J. And this is part C, where we will talk about speech and what to do with the signals before we can feed it into a machine learning model. So what we'll be talking about is MFCCs in specific, uh, which stands for Mel Frequency Sepstral Coefficients. Now, this is a real mouthful, so we will break it down eventually. But before we get there, MFCCs are essentially a really good extraction of information out of speech signals. And these have proven to be very useful, especially in speech recognition tasks, which is what you'll be doing throughout your course for a large part of it, at least, right? So for this recitation, I'd like you guys to keep 3 points in mind as we go. One, speech signals can really be understood as a mixture of signals at various frequencies. So for example, if you have a recording of a cat's meow and you find out that it's really a 10 kilohertz frequency recording, what's really happening under the hood is perhaps it has a whole host of frequencies going from 100 hertz to 100,000 hertz. And it's just that the most prominent ones are the ones at and around the 10 kilohertz point, right? So to wrap it up, you can look at any signal as a combination of a lot of signals at a lot of frequencies. Right? Second point is that, and this is a recurring theme in this presentation, that raw speech signals aren't always the best thing to feed into your model to do any sort of task. And there are two reasons behind this. One, this data often contains a lot of noise, so we want to clean that up at least. The second point is that these signals are naturally continuous, right? And machines don't do very too well with continuous information. So at the minimum, we want to turn it into digital information and then discretize it into chunks. Because our task is speech recognition, what that entails is at the very minimum, understanding what sound was produced. And then from there on, we can do some more processing to find what words were spoken, for example. But again, at the minimum, this sort of discretization does need to be done. And this brings us to our third point, that if you do this discretization recklessly, it can add some unwanted noise in the high frequency bands of your signal. Now, why this happens is really a question rooted in physics and speech processing, signal processing, and we will defer that to some other time. But yeah, with that, let's dive into the term, which is Mel frequency substrate coefficients. The first thing I want to focus on is really Mel frequency. And what you need to know at this point is this is a very nice transformation of a signal to mimic the way humans produce and perceive sound. So the way humans produce sound is not linear. What I mean to say is the amount of energy which is contained at the different frequencies is not the same. We tend to have a lot more energy in the low frequency bands than the high frequency bands. And this sort of transformation really mimics that really well. Next, let's look at the word coefficients. And this should tell you that what we'll get out of this whole process is a bunch of numbers describing the signal at various points. And the last word is quite funny, actually, that I found its etymology. So it's sepstral comes from the word sepstrum, which refers to a spectrum of a spectrum. I mean, we can get into it later about what that really means. But the funny part is that if you look at the function at the bottom, it's C of x of t. X of t is really just a mathematical definition of the signal. C stands for the sepstrum of the signal. And what's on the right is how it's produced. You take the inverse of the log of the function on the signal. The function here is a Fourier transform, and we'll get into it later. But since you apply the inverse of the function you apply inside, they decided, or the people who researched this just decided that it's fine if we just flip the first half of the word and call it sepstrum instead of spectrum. There are a whole host of terms associated with this, such as Q-frequencies instead of frequencies, or harmonics instead of harmonics. It's kind of funny, but yeah, that's how it came to be. So with that, let's really look at how these are produced. And the process kind of looks daunting. So it works if we kind of break it down into three sections. The first section here in blue is done in preparation for the actual MFCC extraction. The second stage in red is how the Sepstral is really produced. Third step is nothing but a conclusion to everything that we've done so far. So let's dive slightly deeper. Now, stage one starts off with your regular old conversion of your analog signal to a digital signal. This doesn't need much explanation. It's really done so that your machines can actually process this data. The second step has to do with the fact that when you look at the speech signal as a bunch of like a spectrum of frequencies, you find out that when humans speak things, they tend to not have a lot of energy in the high frequency bands. And we want to boost that energy so that we can look at the whole signal and then work with that. And we've seen, our research has shown that this really helps with the speech recognition task a lot more. The last part has to do with the discretization step we talked about. So we make windows of 25 milliseconds and place them 10 milliseconds apart. And then we try to find out what's being spoken. The reasoning behind these numbers is rooted in the average speaking rate of a person and the amount of phonetic content or phonemes which are contained in each word that's spoken. And this combination of 25 milliseconds and 10 milliseconds really works well for speech recognition. The thing to focus on, however, is that these aren't just rectangular chunks of windows. They're rather sinusoidal, so they're smoother. And the reason why that's done is so that that noise that we talked about because of discretization, that doesn't occur. Right? So that's a safeguard, essentially. Once we've done this, we can move on to actually extracting the Sepstral. The first step is to apply what's known as a Fourier transform. What we apply is called the digital Fourier transform, since we're working with digital signals. And what it does really is it brings your signal from the time domain. For example, how much, what the amplitude is at every point in time, you map that exactly without any loss of information to how much energy is contained at the various frequencies in your signal, right? Once you do that, and this is done so that we can do the next few steps more efficiently, it's easier to work with frequencies than it is to work with time. And what we do next is we apply what's known as a Mel filter bank, and also some natural logarithm here. And the reason here has to do with how humans produce and perceive sound in a nonlinear fashion, which is kind of mimicked by the natural log function. And these filter banks allow us to separate the different frequencies. This is why we initially converted our signal from time domain to frequency domain so that we can actually work with the different frequencies. Right? And the last step is what really produces these coefficients, is what's known as an inverse digital Fourier transform, in which we map our signal back to the time domain, but this time we do it selectively because we know what areas are of more importance. And out of this, what we get are 12 sets of coefficients describing the signal. And to these 12, when we add what's known as that energy term right there, we get 13 different features. And further, we can take the first order and the second order derivatives of these 13 features, and we can have access to 39 features in all. Now, this recitation was really meant to make sure that you are aware of what kind of data you're working with. Of course, if you have a background in signals, in physics, this would be a lot easier for you to digest. But regardless, the whole idea is you don't need to know perhaps anything more than this, at least at the level of what you'll be working with throughout your semester. Of course, we encourage you to learn more. It's always super interesting. And if you have more questions, we are here to help you out. Perhaps Professor Biksha would be a much better target for questions which relate to this. But sure, we are also at your service. And with that, I wish you a hearty good luck for the coming semester. And yeah, we're here for all of you guys. So see you soon.